then the arc length is 2 pi r. So that's the relationship between the arc length r and theta, which tells me that this distance here is just going to be my radius, which we'll call r times 2 times phi, because that's the angle, as long as phi is in radians. So if I'm traveling at some speed v, I know that's distance over time. My distance traveled is 2 phi r divided by time. And so time is 2 phi r over v. So I can make that substitution over here. At least eliminate one of my variables. Now granted, I throw in another variable, but one step at a time. So 2v sine phi divided by 2 phi r over v. Well, I got stuff that cancels out here. 2's go away. And so this becomes v times v sine phi over phi r, which is just my speed squared times the sine of phi over phi times r. Now, the problem with this is I would need to know what's the starting end point. I need to figure out what phi is. However, since phi is somewhat arbitrary, I drew it out like that, but there's no reason phi shouldn't be smaller. Especially if I want to find the acceleration at one specific spot, I want to make phi as small as possible. So now here, let phi go to 0. Now, I am not saying it's equal to 0, I'm just saying it's incredibly tiny. It goes towards 0, it doesn't actually hit it. And then there it is. And so now we bring in what's known as the small angle approximation. So if you got your calculator, put it in radian mode for a moment. And in radian mode, I want you to find the sine of 0.1. What do you get?
0.0998.
Say it again.
0.0998.
What about the sine of 0.5? Sorry, 0.05.
0.049998.
Let's go down one more. Sine of 0.01.
0.0099. Or I guess you could say
How many nines?
4
And then what?
and 8.
Notice that the sine of the angle and the angle itself are really close to each other. The three significant figures are the same there. Sorry, that would be two significant figures. The three significant figures, they're the same. To 6 significant figures, these are the same. So the small angle approximation says that if theta is small, and again, theta is in radians, if theta is much less than 1, that's just another, that's the fancy way of saying if theta is small, then the sine of theta is approximately equal to theta, which is also approximately equal to the tangent of theta. Because if theta is small, the cosine is really close to 1. Tangent is sine divided by cosine, so it's basically sine divided by something really close to 1. So our derivation now is, if phi is small, this becomes v phi times phi over r, which is just v squared over r. That is the magnitude of the acceleration for something traveling in a circle. Question is there. The direction, which I pulled out before because it was just in the way, the direction is towards the middle. It's in the negative j direction. If I were over here, it would be still towards the middle. It's always towards the middle. When I was swinging the thing, the stopper on the end of the string, there was tension basically pulling it in. Every time the stopper tried to get out, the string just pulled it right back in. Insert your own Al Pacino imitation. And if you don't get the Al Pacino reference, you should watch Godfather 3. So the acceleration, this specific type of acceleration, negative v squared over r hat. Now r hat is a specialized unit vector. I hat and j hat, those are basically rectangular. In other words, there's an I hat direction and a j hat direction. R hat's a little bit different. It's specialized in that it's known as a radial unit vector. So r hat is away from the center. So negative r hat would be the opposite, or toward the center. Questions to hear? All right, vocab. So as I was swinging that thing around, I had this force acting on it, the tension acting on the stopper, pulling it towards the middle. The stopper wanted to travel in a straight line, but I kept pulling it back. This force, pulling it towards the center, has a special name. Yeah, it's tension in that particular case, but in general, its special name is centripetal. It is a centripetal force, which is the force which causes something to travel in a circle. Therefore, this acceleration right here is centripetal acceleration. So when we get into circular motion problems, when we get to the substitution phase, we now have a third thing. We've got weight is equal to mass times acceleration of gravity, W equals mg. We have friction is equal to mu times the normal force. And now we'll have acceleration for circular motion problems is equal to v squared over r. Questions before I talk about that other word, that It's so badly misused, we probably should not speak of it in this class after today. So let's talk about that other word. Centrifugal, or centrifugal. That's what you're trying to emphasize there. In my opinion, centrifuge should be called a centripetal, but let's talk about what centrifugal force is versus centripetal force. So an overhead picture of by swinging the stopper. If I did a force diagram here, I have tension at the end of the string. There's tension pulling on the stopper, and then something holding the string over here. The force that's causing the stopper to travel in a circle, it is this force right here. It is pointing towards the center. It is centripetal force. From a linguistic point of view, centri means center. Clever the way that worked. Petal means seeking. PET is the core there. What English words do we have that have PET in it, where the PET comes from this idea of seeking or coming together?
Say again, sorry.
I'm looking for an English word where PET is in it, that comes from a root meaning that seeking or coming together. In sports, two teams come together. What is that called?
Competition.
Yes, competition. The PET in competition comes from this exact same root. Centrifugal, yeah, that still means center. Diffusion means fleeing. Trying to get away from the center. What English word do we have that has F-U-G in it that means trying to get away?
Fugitive.
Fugitive and,
Refuge.
I would not be surprised. I hadn't thought of that one. Fugitive is the main one I was thinking of. There's also a Latin expression that I've heard many places. Tempus fugit, means time flies. So the centrifugal force in this situation is actually acting at the end of the rope here. It's what's keeping the rope stretched. Centrifugal also shows up in what's known as a non-inertial frame. If we tried to analyze the swinging the stopper from the stopper's point of view, centrifugal force would show up there. And there's comic strips on the wall outside my office which talks about that. All right, any questions before I erase centrifugal and we never talk of it again? All right. So that word, which shall not be named, can be used properly, it's just usually not. Any of you played corners when you were kids? In the car, goes around the corner and you just over exaggerate. All right, got a couple people here. What was throwing you to the outside? What's that? The curve had some magical spell on you? Now, you went to the outside of the car because of the curve, but the curve wasn't actually physically throwing you to the outside.
How fast you going around the curve?
Oh, that definitely has an effect there. But what is the force that is throwing you to the outside? And it's sort of a trick question.
The centrifugal force. You fleeing from the car.
And this is where it's being misused. Thanks for demonstrating how it should not be used.
Is it gravity?
No, that's trying to take you down.
Oh, okay.
I hope that's not the force that's affecting you. I guess if you'd gone over a cliff on a curve, then you would probably be here. The reason why I say it's somewhat of a trick question is there is no force throwing you to the outside. There's nothing throwing you. The question is, why do you actually stay in the curve? Well, there are forces keeping you in the curve. Nothing's making you go to the outside. What's happening there is you're in a car and you're sitting in the back seat in our scenario here. You want to go this way, but the car is turning. So because of the inertia that you have, because you want to go in a straight line, it appears like you're going to the outside of the car, but the car is actually just cutting you off. When you're driving, the centripetal force is friction between the seat and your butt, friction between the back of the seat and your back. Your hands on the steering wheel, you got some normal force going on there. Actually, there's some tension and compression going on there. As you're holding yourself in. Now, if you're going slowly, you are being responsible. You're not necessarily going to feel it. It's not going to notice anything special there. But if you take it at too high a speed, you'll be feeling something. What is the centripetal force when your car goes around a curve? What is the force that makes your car go around a curve? What are the forces acting on a car when you're driving? We'd stop it right there. That answers the other question I asked. If you've ever driven on ice, you know taking a curve is not easy because friction is the centripetal force. It is the force that causes you to be able to actually go in a curve. And in terms of forces on a car, it's friction, weight, and normal. Those are the three. All right, before we start doing an example actually using centripetal acceleration, let's take a break, stretch your legs. All right, so we have this problem here. I have this mass that's swinging around in a circle on a frictionless table. I have some mass M2 hanging down below, basically creating a tension in the string. If the string broke and mass 2 fell, mass 1 would just go shooting off at a tangent. But instead, mass 2 is traveling in a circle. And the big clue that it's a circle is that, what is the speed so that M1 maintains a distance, a constant distance, throw that word in there, a constant distance from the hole. In other words, it has a radius. So that's equal to R. I'm going to simplify it a little bit. The force diagram, all I really care about are the forces acting on mass 1 and mass 2. We're going to go through the exact same steps that we have gone through several times before. See, some people are still writing down, so the question that we'll start out with is, what's the first thing that we do? Yep. So I got my force diagram checklist. Still going. So what are the forces?
Or we just taking into account the boxes?
Yeah.
Okay.
I mean, the table's still there. We're not necessarily drawing the pairs.
What I'm asking, I guess, is there's no rope for,
Do you want me to throw the rope in?
not necessarily.
Yeah. The rope is there even though I haven't drawn it.
Yeah.
Yeah.
So the same tensions there.
Yeah. Which way is the tension acting on mass 1?
Towards the hole.
It is towards the hole. So I'm going to capture this at this moment right here when it's to the right.
Okay.
So I think on a test where I was wanting people to draw a force diagram, I said draw the force diagram when the object is furthest right, just so that it becomes clear which way the tension has to go. All right, so I have tension acting that way on mass 1, and what about mass 2? I will go with the finger gesture. All right, so those are the tensions. There's only one rope, so we got tension at both ends. Tension, done. Can we get rid of anything? Now, occasionally I have a student who wonders, but there had to been something to get it going. And to that I say, no, there doesn't. Some particles come into existence already moving. And so I've just created a situation here where they're already moving, just like that. Right, anything else we can get rid of?
Friction?
Yep, that's what that was. I guess I can put an X next to the O and F. All right, Normal. What is the requirement for normal?
Contact.
Okay, is there anything touching anything? I agree with you, Craig.
M1 to the table.
Yeah, there we go. Yeah, mass one and the table are touching each other, so which way is the force, normal force acting on mass one? And then down on the table, but we're not drawing the table part. And then that's it for normal. Mass two is touching the rope, but that's why we have tension there. And gravitational.
Pulling both of them down.
So I have weight one, and then over here, weight two. All right, I did not state this before, but mass two is in equilibrium. From a practical point of view, at least as close as we can get. We'll see if I can sort of, I can demonstrate it partially. It's in the wrong place. And that is two.
There's only one metal tube.
That's all I need right now, but. I just gotta put that in the wrong place. Now, the lab that you're gonna be doing probably next week, and that involved this. And my first year here, I had not found rubber stoppers, so we were using metal weights or masses for the end piece here, and the string broke. So I didn't realize I was standing right here, and suddenly there's a huge smack against the wall here as the metal went flying across the room. Fortunately, no one was hurt. All right. Now, there is friction here that is keeping it from sliding, because otherwise this would slide down. There we go. Got caught on something.